Great.
Okay, our final speaker is plenary session is Nora Luca, who is professor of psychology and James H. Blackman Distinguished Faculty Fellow at Temple University. She is also the principal investigator of the Spatial Intelligence Learning Center, also known as SIL.
Thank you, Tim, and it's wonderful to be here in a country I've never visited before, which is very, very interesting. So thanks for inviting me. So I often speak to people about spatial cognition and spatial development, and I've come to be aware that there are two very different kinds, I think, of spatial cognition. There's a distinction to be drawn. It's somewhat similar to what Barbara said about geometric and functional. I think it's a little different. There's a distinction to be drawn between spatial cognition in the sense of navigating or finding one's way in a wider environment, and spatial cognition in which people manipulate objects. They rotate them, they fold them if indeed they can be folded, maybe they cut them if they can be cut. And there's quite a lot of work on how people do tasks of each kind. But one interesting contrast is that navigation in the environment has mainly been studied normatively. How do rats do it? How do humans do it? How do human children do it? Whereas mental rotation, paper folding, and so on have been studied normatively to some extent, but there's also been a big emphasis on individual differences. Many of these kinds of tasks have been turned into tests, where some people go more slowly than others, they can't even do the difficult items, and then there's been an effort to look at what those tests predict. Now, we all know that some of us navigate more effectively in the wider world than others, but that's been less studied, and I think it's time for it to change, and it has been changing. And in fact, I think that the study of individual differences in what's been called the cognitive map may be key to addressing what has been a debate as to whether there even is such a thing as a cognitive map. That is, I think some people under some circumstances form such integrated representations, and other people have more difficulty. So I want to talk about that work. I'll begin to touch on development towards the end of it, although I only have a little bit of pilot work on that. And then I want to talk about three classic theories of spatial development in the navigation domain, and then transition briefly to a fourth approach that I've been advocating, which is called an adaptive combination approach. So that's the plan of the talk. Now, many of you may know that cognitive maps are a term that's been around for a long time, proposed by Tolman a century ago, used by O'Keefe and Nadell in their well-known book, The Hippocampus's Cognitive Map. And many of you also know that the cognitive map has come under attack. It's been questioned by findings of biases and distortions, for instance, in people's spatial judgments. So, for instance, many people believe that South America is directly south of North America, an inference that seems to be licensed by the fact that they're called North and South America. But in fact, they're not perfectly aligned, so that the west coast of South America is aligned with the east coast of North America, and people make strange errors in judging the relative locations of South and North American cities because they don't recognize that. And there's actually a big literature on these biases and distortions that I don't want to go into. I simply want to note that this is the kind of finding that has led many people to suggest that people's representations of the wider environment are categorical or associative or non-metric or in some way definitely not a map. Now, the approach that I've been taking recently was actually pioneered in 2006 by Teru Ishikawa and Dan Montello, who published an article in Cognitive Psychology that suggested exactly what I proposed a minute or two ago, which is that some people are really good at doing this. Some people can learn to do it, but they're not so good at the beginning, and other people simply don't seem to form cognitive maps of their environments. So they suggested this in the context of an experiment done at UC Santa Barbara, in which they took students into the hills above Santa Barbara, which, as you can see, are folding and undulating and not the kind of terrain that it would be very easy to form a cognitive map of. And they drove, or rather, I believe Teru Ishikawa drove, these undergraduates on one U-shaped route there, on another, taking by a circuitous back way, took them to this S-shaped route down there, and then at some later time took them on the route that connected the two routes. And then there were a variety of measures, sketch maps, pointing judgments, and so on and so forth. I'm not showing you the data, but the fact is that many people could not learn this environment at all, even when they experienced the connecting route. Some people didn't understand it at the beginning, but by the end seemed to have formed an integrated representation. And other people, possibly, you'll be surprised by this because it's really quite difficult, were able, even pretty much from the beginning, to integrate the two routes. So we thought this was a very intriguing approach, but we wondered at how many people failed to learn, which is a little disheartening if you'd like to help people learn better, and thought that it might be for two reasons. One is that the subjects, the participants, were passengers in a car, and it's well known that passive interaction is not as good as active guidance of yourself through the environment. And another fact is that they only had one connecting route, and people often represent junctions as right angles, and in fact you can see that those are not right angles. So if you get the junction wrong, then it's very difficult to really relate the two routes. So we went on to do an experiment in which people had to walk. So this was active self-guidance through the environment. It was done at a campus of Temple that's out in the suburbs called the Ambler campus, which very few main campus students have visited. So we took students who had not visited the campus, and we took them along one route, a U route there shown in blue. We took them along, oh, and by the way, they transitioned from this route to this other route. They were put in a wheelchair, they were blindfolded, they were made to wear headsets in which music was being played, so they didn't directly experience the connection. And then they experienced this yellow route. So there's 4 buildings on the blue route, 4 buildings on the yellow route. That happened on day 1. Then on day 2, they had the same experience, and they experienced one of the 2 connecting routes. And on day 3, they had the same experience and experienced the other connecting route, and which connecting route was counterbalanced. So what we found, I'm just going to show you the results from one dependent variable, which is off-site pointing. In this task, you have to imagine that you're standing at a specified building in front of it. And as people were taken on walks, they were shown that this is where you're supposed to be imagining standing later. And they had practice at doing these tasks. So imagine you're standing in front of this building, point to that building. That's a between route judgment. Imagine you're standing at this building, point to that building. That's a within route judgment, but you can't see those 2 buildings one from the other. And what we found over the trials is shown in this graph. So First, the within root judgments, which are the easier ones because you've experienced them on the same journey, start out with about not a little less than 40 degrees worth of error and get slightly better. There's significant improvement when you experience the first connecting root. What's more striking is that the between root judgments are not very good at the beginning, but they're not bad either. They're up at 60 degrees of error, and there's steep improvement after experiencing the first connecting root, so that at that point, and also after experiencing the second connecting root, there is no difference between root and within root judgments, which does suggest that the people had integrated the two roots and related them one to another, which is one of the indications of forming a cognitive map. Now, you'll also see that there are error bars. There are enormous error bars around trial 1 for the between root judgments, and there are substantial error bars around trials 2 and 3. Now, looking at trial 1, you might wonder how anybody is very good at this task at all, because you haven't experienced a connecting root. But this illustrates that there are always cues in the natural environment that you can use. This is a main road, so if you keep track of where that is and think that the campus is only on one side of the main road, that constrains where the two routes can be in relation to each other. The blue route is up a hill and down a hill. There's a slope. This is flat. So if you combine the main road with the slope information, which some people use and some people don't, you can also draw an inference. This building, the white one in the middle, which is called Bright Hall, has actually a very different facade when you view it from this side versus viewing it from that side, but it does have the same outline. So if you pay attention to that, you can integrate the two routes. And lastly, there's the sun. Now, the sun wasn't always shining because we did it even when it was cloudy, but in some cases you could use the sun. So people differ in that. Now, even when you look at pointing on trials 2 and 3, there is variation. And pointing on trials 2 and 3, turns out we did structural MRs on 13 of these 16 participants. And it turns out that just like the London taxi drivers that some of you may know about, although there people have always wondered about self-selection, these are just ordinary undergrads who are learning this environment for the first time. And the people with a larger, especially right hippocampus, had lesser errors. So that's another finding of that kind. And it's actually also along the anterior-posterior part of the hippocampus, so that the center of gravity is different for the people who do better than the people who do worse. This is mediated by perspective taking. The people who do better and have larger hippocampi do better on Mary Hegarty's perspective taking test. And then I'm not showing this finding, but the size of the caudate nucleus also predicts, except in the other direction. People with a large caudate have high errors, and the caudate nucleus is associated with focusing on just the feel of the route, on turning left and right. So we have pretty striking individual differences that are correlated with the brain. But one of the things that we wanted to do was to be able to test more people. 16 people is a very small number of participants. And doing this work was a big effort. Getting them out to the campus, you can't run the experiment if it's raining, pushing them around in wheelchairs, this is a nightmare. So we decided to construct a virtual Ambler, which we are now calling Silkton. Victor Shinazi made this. He's a very gifted VR creator. It has the same footprint as Ambler, but I hasten to say that the buildings at Ambler don't look this charming. He just made them beautiful. People follow this around. It's just a desktop VR. They follow the arrows. They can't go off the route because they hit invisible walls, although we have now made a free exploration version of this VR. But in this experiment, they follow the route, And then they're given the pointing task that I described before. So you imagine you're standing at a certain point and you have this kind of rifle sight and you have to point to, say, Harvey House, and we look at how accurate you are or how much error you show. And what we found was that some people, who we called integrators, these are the people who are forming cognitive maps, have reasonably small error both for within root judgments, which are shown on the y-axis, and for between root judgments, which are shown on the x-axis. Then there are people we are calling non-integrators who are still doing pretty well on the within root judgment. In fact, they're doing pretty nearly as well as the integrators, and they're not doing so well on the between root. They know the roots, but they don't know how the roots are related. By the way, 90 degrees is chance for this measure, so some of them are getting dangerously close to chance for between root, although they're not all at chance. And then we have people who we are politely calling the confused, who have not only high degrees of error on the between root judgments, but also pretty high degrees of error for the within root judgments. And various types of cluster analysis all converge on this kind of three-group solution. So some of you may know that there's a self-assessment of how well you do at navigating around the world called the Santa Barbara Sense of Direction Scale. It turns out the results for the Santa Barbara Sense of Direction Scale are these. The people in green are the integrators, and they rate themselves highly. They're good, they know they're good, they tell us they're good, that's great. The people who are the non-integrators and the confused, both groups rank themselves low, and that is not a significant difference. So the Santa Barbara Sense of Direction Scale is actually not picking up on the potentially important difference between people who can at least learn the root and people who seem not to even know that. Now, we also have some other measures. Here's perspective taking, which I said did work in real Ambler to differentiate the people who were good from the people who were bad. Here again, the integrators are better than the other two groups, but that is actually not significant in this experiment. It is significant that the integrators have better mental rotation than the other two groups, and it's also significant, but this is just another dependent measure, that the integrators build better models of the environment. So there's a couple of things you may be wondering about. One is, are the integrators just really, really bright and the confused are really, really dumb? Is this just global intelligence? We had one indicator at this point that that was not true. This is self-rated verbal skills, so it's analogous to the Santa Barbara Sense of Direction Scale. And they really don't differ in their self-evaluations of verbal skill. Another thing you may be worried about is that the non-integrators and the confused don't look different on most of these measures. I mean, sometimes the confused look a little worse, but those paired comparisons are not significant, so maybe we have a false dichotomy there. Maybe the Santa Barbara Sense of Direction Scale is telling us the real story, that they're bad. So we've now followed up with more virtual Ambler, more Silkton subjects, and we've acquired some other measures. One of them is verbal working memory, where you have to do some math, remember a letter, do some more math, remember a letter. The math is unimportant, but ultimately you have to be able to say A, D, but it goes up an F and W, and we see how high you can go. And also spatial working memory, where you have to judge, is that design symmetric? That's a filled square. Is that design symmetric? That's a filled square. Look at a blank matrix, which are the filled squares? And again, you go up to more and more and more filled squares. So we got those two measures. We also did a task of root membership. We were wondering whether the integrators, the people who form cognitive maps, have lost the roots. Do they just integrate them so well that they really forget which buildings are on which root? Or are they holding the roots very firmly in memory but know the relationship between the roots? So this is a task where you're shown pairs of buildings. You have seen all of these buildings before, so this is not a yes-no judgment at all, not a recognition judgment. Instead, for each pair, you simply have to say, were these two buildings on the same route, or were these two buildings on a different route? And then we also got an objective measure of verbal IQ, which is this WRAT measure. Here are the findings. It's still in progress, but we have a lot of subjects and we're feeling pretty confident. I'm not sure why we have different colors here, but we have the integrators, the non-integrators, and the confused. And what we see now is, and I don't show the objective measure of verbal IQ. That is not different. So that confirms their self-reports. These are new participants, but it confirms the reports of the old participants that they have the same verbal ability. They turn out objectively to have the same verbal ability. In terms of verbal working memory, which is not the same thing as verbal IQ, we now have the non-integrators doing definitely better than the confused. So one of the things that may be helping the non-integrators to at least learn the route is their verbal working memory. On spatial working memory, the only significant contrast is between integrators and confused. Similarly, the only significant contrast here is between integrators and confused, but you'll also see the answer to the question I posed earlier: do the integrators know the route, or have they lost the route by integrating the two routes? The answer is these are the people who really know the route. They know the route cold compared, well, I wish that one was significant, but not really, but that's intermediate. But they clearly know the route very well, and they simply are then additionally representing the relation between the two routes. Let me just say before I turn to the work with children, because I know some of you are interested in Amy Shelton's individual difference measure, that we've also given these participants the Shelton measure. And the relationship between the Silkton assessment and the place response measure you get from Amy's work is quite complicated. If you want to know what it is, ask me later. That's why I didn't put it in here. So there's lots of individual differences out there to be assessed, and I think this is a, hopefully growing enterprise. I think it's going to be important. Now, we've recently started, and this is very piloty, to look at 8 to 11-year-old children, and they're the purple squares here. And you'll see that 8 to 11-year-olds, and they're pretty old, and they play a lot of video games, so I don't think it's that they're having a problem with the VR. They're all confused, and it doesn't really seem to even be correlated with age. I mean, the 11-year-olds are maybe moving a little bit down to the red area where they could become non-integrators who know the route, but we changed our IRB so that we can study 13, 14, and 15-year-olds. We think this ability may come in pretty late, and this actually confirms work that a guy called Alex Siegel did many, many, many years ago with real environments. Developmentalists are used to thinking, I was used to thinking for a long time of 8-year-olds as practically geriatric, but 8-year-olds may be merely at the start of being able to form these kinds of cognitive maps. So that's what I wanted to say about individual differences. I quickly wanted to go over 3 general approaches to spatial development and transition to a 4th model, just to do a little bit more on development, since I promised I'd say some things about development. So I often find that people who don't study development but are interested in spatial cognition know at least one of these 3 approaches. So that's why I wanted to address it for this audience. One is Alex Siegel and Shep White's sort of classic chapter from 1975, in which they proposed that initially you learn landmarks, then you learn routes, and then you construct a survey map. And essentially I've already dealt with that in presenting the within route and between route paradigm. I think it's not exactly wrong, because landmarks and routes and survey maps are concepts that we use use in discussing navigation. But it's not exactly right either. It just leaves a lot out. For one thing, it leaves out inertial navigation or dead reckoning. It leaves out body-based cues, which I think Tim is going to talk about tomorrow. There are many kinds of landmarks, and Siegel and White don't really address this. So there are landmarks along the route, but landmarks at choice points are very different from landmarks along the route. There's also landmarks, distal landmarks, that help to keep you oriented in the wider environment. There's also geometric boundaries, which have turned out to be very important. And then, of course, there's, as I showed, wide variation in to what extent individuals form survey maps. So these are some of the developing themes that I think make Siegel and White a pioneering effort, but not one that, really is a contemporary theoretical framework. So the other two things that people often know about, if they know nothing else about spatial development, are Piaget and Liz Spelke's proposals about the geometric module. And I want to just talk about them quite briefly, each of them. So if we go to Piaget, he said that metric coding of space appears very late. The children initially only know topological space, whether things are touching or not. Those of you who were at Alex Klippel's talk know something about topological concepts. And projective and Euclidean concepts are only formed at about age 9 or 10. So a lot of work, including some of my own fairly long ago work, was devoted to questioning these ideas. But after a few slides in which I question the ideas, I also want to mention what I think is right about the Piagetian approach, because just as Siegel and White provides some useful concepts, I think there are some elements of Piaget that were not wrong. But first, what is wrong? So in the 1990s with Jane Ellen Huttenlocher, I did a couple of papers in which we showed that young children could estimate distance metrically. In the experiment at the top, which was with children between 18 and 24 months, we hid toys in a 5-foot-long sandbox. We smoothed over the sand, twirled them around. Adults who come in can't tell where the toy is buried, and we asked the child to find the object. We coded where they first touched the sand, just because that's an unambiguous response. And what we found is that where they first touched the sand correlated very, very closely with where the center point of where the toy was actually buried. We did a similar but different experiment with 5-month-old infants who are too little to walk and don't even grasp very well and therefore aren't good pointers. So we sit them in an infant seat, we show them something being hidden and coming out, being hidden and coming out. After a few trials of that, being hidden, and for the experimental group coming out of a different spot. And we ask if their looking time is longer when the toy emerges from the spot at which it was not hidden. And we find that indeed they do look longer at those events. In another line of work that makes more contact with work with rats and mice, we also found that very young children have much better spatial cognition than Piaget would have imagined. This is a paradigm called the Morris water maze, in which Richard Morris, to start with, threw rats or mice into round containers of milky water. Rats can swim. They don't like to swim. There's a hidden platform that the rat can't see because the water is milky, but when the rat gets to it, the rat clambers thankfully out of the water. I can quit swimming now. The rat also does something quite interesting. The rat kind of rears up as much as it can and it looks around at the surrounding landmarks in the room. So here we see the round container in a room just with window, file cabinet, door, these kind of things. And then the rat, sad to say, is thrown into the pool from a different approach. So it can't just swim forward and then turn right or whatever, but having looked at these landmarks on the side of the room, it is, after a few trials, there's some learning, able to navigate to the hidden platform. Doing so requires our old friend, the hippocampus. So we have found that there are changes in place learning in human infancy. This is an older study that used the sandbox paradigm. You can see that there are white circles around this sandbox. We removed the white circles for a randomly assigned half of the children and took the children around to the other side of the sandbox, which means there's more error than there was in the graph that I showed you earlier. They're still pretty accurate, but they're just more slop in their estimates. But for the 16 to 21-month-olds, they don't do better or worse, depending on whether they can or cannot see the doors and the windows and the stuff in the room. By the time they're 22 to 24 months, it makes a big difference. Without the curtain, they use the landmarks in the room to zero in more successfully on the correct location in the sandbox. And the same is true for 28 to 36-month-olds. Now, this has now been replicated by several people. One is the Lavenet lab in Lausanne, which is actually where I was just before I came here. But this is a study that we've done more recently, which actually uses a pool, except there's no water in it. IRBs frown on throwing toddlers into actual pools. And instead what we did is to have tiles in the bottom of the pool, and a puzzle was hidden under one of the tiles. The animals are taken out of this puzzle, and the puzzle itself is hidden under one of the tiles. So you can't see the puzzle, you can't feel the puzzle, and the child is introduced into the pool from a variety of locations, just as with the rats in the Morris Water Maze, and asked to find the puzzle. Here's a cow. Where does the cow go? Can you find where the cow goes? And what we see, if we score either the X marks the spot, did the child go to the correct tile, or we score the penumbra around X marks the spot, which is the air, it's not so bad, at least you didn't go to those white tiles. So both for going to the gray squares and for going to the X marks the spot square, there's a very marked difference between 16 to 20-month-olds and 21 to 24-month-olds. Now, you'll see that adding these two together, the ones who are not quite 2 are not perfect at this, but they're much more reliably going to at least the correct area than the children who are younger than 16 to 20 months. Now, why is this? There's several possible causes, and I don't think they're mutually exclusive. One of them is hippocampal maturation. We used to think that the hippocampus was very mature at birth. This was proposed by Adele Diamond and by Chuck Nelson. But actually we now know, and actually the Lavenet lab is this graph is taken from some Japanese researchers, but the Lavenet lab has shown this very clearly. There's an extremely steep increase in the first 2 years of life in hippocampal volume. And so that could be part of what's going on. Another thing that I think is relevant is a consideration that I take from research by Karen Adolph. Children, as you may know, don't learn to walk upright until around 12 or 13 months of age. They don't do so really steadily until a few months after they start doing it unsteadily and kind of plopping on their bum every once in a while. And what Karen has done is to attach cameras to kids' heads so that you can see what they see when they crawl. That's all they see. This is a long sort of chute she has in her lab. The stripes are so that the camera can really visualize where they are. Crawlers look down. They only see the sort of gangway in front of them. Here's a crawler, that's what he's seeing. This is what the adult thinks the kid is seeing, but it's not what the kid is seeing. Once you walk upright, you can actually see those distal landmarks that are what you need to succeed in place learning. So it may not be an accident that hippocampal maturation is tracking upright walking. This is why I said these are not mutually exclusive explanations. Once you have to be an upright walker before you need a hippocampus that can do this, so they may as well track each other. There's also a possible clue that we've talked about in this symposium already, which is spatial language. So we had parents complete an assessment of their children's language, and we found that place learning correlated significantly, albeit only 0.38, but significantly, after controlling for age and after controlling for some aspects of their search behavior, so getting rid of some confounding variables, with knowing prepositions. It did not correlate with knowing nouns, it did not correlate with knowing verbs, it correlates only with knowing prepositions. Now, this is a little bit a mystery to me, though, because when you look, I think you can't see, but this is just a listing of how many kids knew what prepositions. So the only really high bar is for up, the next one is down, the next one is off, the next one is inside or in, and they go down pretty quickly. So the kids don't know many fancy prepositions. They know, I mean, they're young. They're 18 to 24-month-olds. They know some basic prepositions. So it's not clear that spatial language is helping them by allowing them to verbally code where the puzzle is. Instead, I think it may be a sign that they're more spatially sophisticated and they're able to learn the language, or you could turn it on its head. If they are learning the prepositions because maybe their parents are using them a lot, maybe that's making them pay more attention to spatial aspects of the world. That causal arrow could go either way. Now, this is the last thing I have to say about Piaget, and this is where I want to rehabilitate him a little bit. He wasn't wrong about some aspects of spatial cognition being late. So I'm picking only one here, perspective taking, and this is one that I myself have published a task on which 3- and 4-year-olds can succeed at doing something like perspective taking if you ask them the question just the right way. And this is not just what's called, if you know this literature, level 1 perspective taking. It's actually computing what another person sees. You can get 3- and 4-year-olds, although I don't really think younger, to do this pretty well. But if you do this the way Piaget did it, and we've now made it into an actual test with little Playmobil figures, and the question is, what does this little guy with a camera, what kind of picture would he be taking? And the answer is where this green thing is in front of this pink thing. What you see, very much mirroring the classic Piagetian results, is there's a lot of egocentric errors through 7. They decline at 8. And in terms of accuracy, although the kids do pretty well when, I mean, this just shows they understand the task, when they don't have to move, when it's 0 degrees, in alignment with their own view, they can do it well. But their mean accuracy at both 90 degrees and at 180 degrees isn't really picking up until 8 years of age. Now, the reason I draw attention to this is, number one, Piaget is indeed replicable. If you do what he did, it's replicable. But also because the perspective-taking task that I mentioned earlier that we used in the research with Epstein and Shinazi that mediated the hippocampal volume relationship is a test that Mary Hegarty's made up, which is essentially the Piagetian perspective-taking task, although I kind of actually prefer our measure, and certainly our measure is more kid-friendly. But if you're talking about the sort of perspective-taking task that is supporting wider environmental spatial cognition, then it's possible to me that indeed you have to be 8 before you get good at it. And indeed, remember that at least in our pilot work with the Silkton paradigm, the 8-year-olds are at best confused. So it is part and parcel of this, for me, emerging interest in later childhood and early adolescence, which I think is going to be important. So I also wanted to say just a teeny bit about the Spelke proposal of a geometric module. There's some of you in this audience who've heard me say more about this than you probably wanted to hear. There may be some other people who haven't even heard of it, but I'm just touching on it a little bit. So Spelke has proposed that that children begin with an orientation to the geometry of the environment. And this, I believe, is true. The boundaries in the environment, in this case walls, are very important, but other boundaries such as the canal or the river, which are partial boundaries, which don't completely, as I understand, enclose us, are important aspects of spatial cognition. And that, additionally, she has proposed that we do not, in toddlerhood and early childhood, use other aspects of the environment. We simply rely on the geometry. And this is the part that I think is not exactly correct. So she puts small children, 18 to 24-month-olds, in a rectangular room where the C for correct corner has the long wall to the left of the short wall and twirls them around so they don't know where they are. And they go half and half to the C corner and the R corner, and they can't be blamed for going to the R corner because the walls are all white, they were twirled around, the long wall is to the left of the short wall, so maybe it's correct. So this is evidence that they are using the geometry of the enclosure, a proposition with which I totally agree. The additional finding is that when you add a colored wall or other kinds of landmarks, the children who are less than age 6 do not use it to go to the correct corner. And this is evidence in Spelke's approach for modularity, for an encapsulated or impenetrable cognitive module. Now, adults do not have an impenetrable module. Almost all trials with adults go to the correct corner once you have this colored wall. And Spelke has proposed that language is crucial to this transition. So again, touching on this spatial language theme. In particular, that you need to have the ability to use the words left and right in order to succeed. So this is just one piece of evidence against that idea. This is the result that Spelke reports that I just showed you, where toddlers, 3 to 4-year-olds and 5-year-olds are at 0 in their ability to get off of chance. They go half and half to the correct and to the reversal corner. And suddenly they go more as 6-year-olds and even slightly more as adults to the correct corner rather than the reversal corner when they have the colored wall. But this is in a very, very small room. It's basically a closet. In a slightly larger room, the size of a small bedroom, you see that toddlers do pretty well, 3 to 4-year-olds do pretty well, 5-year-olds do pretty well. It's true 6-year-olds do better, and adults actually do even better. But children who are young enough that we know they do not know the words left and right are able to succeed in the larger room. Now, I've done a lot of work on this topic. There's a paper, if you care to pursue this, on why the size of the room counts. There's a paper rebutting a claim that Spelke made that features are just used associatively in a second step. You can go to an overview of these arguments that Twyman and Newcomb published in 2010 in Cognitive Science. But for now, what I just want to highlight, because this will help me to transition to the last part of my talk and to what I think is the way forward for the study of spatial development. Young Shu, who's a postdoc with Terry Regier and I, are working on a Bayesian model of these data that would allow us to explain the very large and complicated literature, hopefully to make novel predictions, and also to explain why the small room behaves as it does, which I think does cry out for explanation. So this is, I'm not going to tell you about it, this is a stay tuned, but what I do want to tell you a little bit about is the general idea of adaptive combination models of spatial development, which I've been advocating for a long time, beginning with a book that Jane Ellen Huttenlocher and I published in 2000. And the general idea, and I think you'll hear more about this from Tim tomorrow, is that the weighting of the whole rich variety of sources of spatial information in the world depends on factors such as the salience of those stimuli, the certainty with which you've encoded them, the Q validity of those classes of stimuli in your recent past, and that weighting develops both in real time. When you're in a particular environment, you might find something as a good cue or a bad cue and adjust your weighting accordingly. And it also develops over developmental time in childhood. So for instance, recently Gavin Bremner and colleagues have studied reliance on visual versus vestibular information in infants and how that balances and how that gets combined. And I just wanted to mention some new work that takes this approach that is not my own, but I think it bears watching. So Anna Weissmeyer and Lucy Jacobs have done some work on combining cues that uses a paradigm that they've also used with squirrels. Lucy Jacobs works a lot with squirrels, and they have a Bayesian model of the squirrel's behavior. They have yet to have a Bayesian model of the kids' behavior. But what they're looking at are 3- and 4-year-olds who want to know which of 4 boxes contains a toy. And each box is marked with a distinctive object that is beside it. Each of those boxes has a distinctive position on a table, and not pictured in this photograph, each of the boxes has a distinctive relationship to the outside world. So what you can do, and I won't go through all you can move the table but leave the things on the table in their position. You can move the things on the table, leaving the table in the correct position in the real world. You can rearrange the little objects that mark the boxes. You can do all these permutations. And when cues are in conflict, the question is how the kids approach the task. So the short story here is that the 3-year-olds just focus on one. They have a preferred cue, they pick it, and they stick with it. It might be the adjacent toy, it might be the position on the table, it's actually rarely the position in the wider world, but it can be. Whichever it is, they just stick with it and they take no account of anything else. The 4-year-olds at least adopt, this isn't utterly rational and certainly not Bayesian, but they adopt what's called a majority strategy. So when 2 of the 3 classes of cues suggest a particular box, they pick it, even if the one that suggests a different box is their preferred cue. So 2 outvotes 1, even if you like the 1. And that's the majority location data here. So I think these are the kinds of analyses that we need to push forward. The last example of this kind of work comes from Marco Nardini, a paper he published in Current Biology in 2008, in which you're starting here, you're looking actually to place an object in position 1, position 2, or position 3. This enclosure can be made dark. There's cues that can be lit up, or not, and that can be moved or not. So you have to go to the location sometimes in darkness based on your memory of your path, sometimes lit by the cues, sometimes lit by the cues, but the cues are in the wrong place, etc., etc. So the finding here, and this is echoing the later spatial cognitive development finding, the adults do what is rational, which is if they only have self-motion, they have a certain amount of error. If they only have landmarks, they have a certain amount of error. If they have both, they combine them. Even when they conflict a little bit, they take them into account, and the green is the best. And here again, the green is the best. The 4 to 5-year-olds and the 7 to 8-year-olds do not do that. Again, they pick one or the other. So this weighting process, I think, takes different lengths of time to develop for different classes of problem, but it can develop quite late. And so again, we get back to the theme that my 8-year-olds are not geriatric after all. Thanks. Yeah.
I think this is on.
Thank you. I wonder regarding the study with roots and comparing the kids. Basically, they were very similar to the confused sample of your probants. So I was wondering how they would perform if the idiothetic kind of navigation, which of course takes into account the individual movements like number of steps, angle of rotation, how they would actually perform afterwards. I would expect that they would be much, much better.
Right. So, I mean, one thing to say is that the idiothetic or body-based or inertial navigation, or I mean, it has a million aliases, it itself does develop. So, for instance, John Reiser is someone who studied this, but it develops earlier. So by the time you're 8, you are pretty good at this. So your question touches on the question of whether VR is an adequate way to study these kinds of problems. I'm encouraged by the fact that these data, though, do mirror what Alex Siegel found a long time ago, that our data with adults with virtual ambler mirror our data with real ambler. I'm also encouraged, although this is a half full, half empty glass kind of story, by some recent data in which rats were run in a virtual environment and also in a real environment with implanted electrodes that could record from their place cells and head direction cells and so on and so forth. Now, the place cells, fewer of them fire in VR, and they fire less robustly in VR. And on both of those measures, VR is about half the real environment. So, yeah, VR is not the real world, but the place cells are still firing. So that's why I said you could, it's one, it's the other, it's hard to know. I do think that everyone would do better if they were really walking around, but it's just impractical to do many studies that way. So I think it's okay. It's not the best, but it's okay.
But the
follow-up, I think the data you referred to, rats were finding their way in virtual reality that did not provide idiothetic cues. It was kind of like looking at a movie. Isn't that right?
Well, I guess,
yeah, that's the point. Right. Yeah, right. Exactly. Right.
I guess those experiments are run on the ball, which is flotating on the air. So the rat is actually moving. Otherwise, it wouldn't have the theta oscillation going on in the hippocampus. So the idiothetic cues, they are there to some degree, at least for real movement. Yeah.
Wow.
But it's definitely true that the representation, provided by hippocampal place cells is much sparser in these experiments.
Yeah. Okay.
On the other hand, we know actually that the representation of space in hippocampus is developed actually very early in rats and mice. It's only in the age of a couple of weeks, basically.
Right. It's definitely a different developmental timetable. What is in a piece of crazy abracadabra magic, it's 19 to 21 days in rats, whereas it's 19 to 21 months in humans. Yeah. And monkeys are kind of in between, but yeah.
Thank you.
Barbara's, yeah.
I love the idea that a lot of our of the developmental changes we see are driven by happenstance changes of experience. And so I thought of two as you were talking. One is with your memory roots and memory for roots, the within and between roots. What about driving? When you start driving at 16 or 17, I mean, you could even look at it across different states where there are different
Right.
driving.
Right.
There should be, I mean, if driving causes something to happen that's different, you
Right.
could get a really sharp change. So
It's possible. It's also possible that the licensing laws reflect actually when
Intuition, yeah.
people are more capable of, just like the insurance companies got it right with
Yeah.
respect to risk-taking, age 25 to really rent a car, that 16 is sort of a good age. But again, the causal arrow could go either way. You know, if
Yeah,
we get 12-year-olds to drive, maybe they'll learn more. I don't know.
Yeah, it's true. It just occurred to me that once you start driving, I mean, you do start, you know, assuming that you're really learning to drive, you start attending to way different things than you did before when you were
Exactly.
sitting in the car. That was one thing. And the other thing was the thing about spatial language, where you have kids doing lots of ups, which, I mean, the context in which kids use that primarily is up. And so actually that could lead to them being upright more often.
Oh, that's so funny. I never thought of that. Because they do a lot of times use up, up. Yeah, maybe. Oh, that's funny. I never thought of that. Huh. Huh. Right. No, that's the point.
Well, but it's having the effect of changing your posture. So just like we showed with perineal, what do you see in the problem with the standing up? But actually, if you're producing lots of ups, are changing posture more often.
Yeah, it's funny.
I self-identify as confused spatially. And I was wondering if you could say a little bit about why you think working memory plays such a prominent role in the difference between
Working
those.
memory? Well, I think verbal working memory is relevant partly because all the buildings have names, maybe chiefly because all the buildings have names, and you're eventually going to be probed by the building's names. So if you forget, you know, where's the Russell building or whatever, you can't really do the task. I think that spatial working memory is important because as you construct the route, like, okay, I turn, so that means this building is like this with respect to this building. Okay, now there's this new building, so not only where is it with respect to this one, but where is it with respect to that one? So that I would think is more spatial working memory. Yeah.
Hi, I have a question and maybe a comment or speculation. The question is about when you were doing the Silkton study, did you look at exploration styles? Is this a free exploration where people...
No, these are all follow the route ones. Free exploration we created because the Avramidis group on Cyprus wanted to do an experiment with free exploration, so they're actually going to be reporting on that experiment in Bremen. And that could be very different.
Yeah, and I think it's really important for to keep in mind both in the Ishikawa and in yours, it's not exactly like real-world navigation in that you have no control at all. You're driven around or you have to take this route, and in such circumstances, I think people may react very, very differently. Like, I either have to be in control of this, because I know it's correlated with personality things about sort of wanting to be in control, and I need to know where I am at all times. They're taking me to strange places, whereas I could just sit back and let it happen.
Right.
But if we let people explore on their own, we might find very, very different things,
Right.
I think. And the other comment or observations about the developmental story to get you from 8 to 20 I think it's a really fascinating topic, and I agree that I think it's going to be an interaction between their cognitive abilities, personality traits, and experiences in the world, which will also include maps, because I think we find that in the Santa Barbara sense of direction scale, people who rate themselves higher as direction, there's a subscale that they also like maps a lot. And when we're talking about causal directions going both ways, it could be because they have good working memory and they like, or it could be because this is the view of the world they've gotten used to. And integration is obvious on maps and not obvious when you're navigating in the world. So,
Yeah.
you know,
Yeah,
some
I
symbols
totally
will
agree.
matter. Yeah.
And the Shelton measure has correlations with personality. Amy's really done quite a lot of work on that. But I just wanted to correct one thing. They do, they follow the arrow, but they follow the arrows like totally at their own pace. So it's not that they're just drawn through. It's not like a movie. They have to, you know, use a mouse and so forth to go forward at their pace. They can swivel and look at things. They can back up. They just can't get off the route that's marked with the arrow.
But even going back to Tolman and O'Keefe and Adele, for a cognitive map to form, you had to have random access to the points. And without that, I don't know if we should expect that everyone...
Yeah, this is a good point. Well, actually, the Avramides people were interested mainly in gesture, but they may have the data that we'll see next week, right? Yeah.
Can you think of an intervention for the confused people, or do you think they're just lost cases?
We don't. Oh, are they? No, I don't
they?
think they're lost causes at all. But that's my faith in, you know, plasticity and malleability, right? I'm like Ms. Malleability. I very much think that people can get better. They just have to learn, you know, there's certain tips. There's a CBC guy who made a film on this kind of disorientation, and it's called Finding Your Way, I think. I forget what it's called. And he had various spatial researchers construct a list of top 10 tips for not getting lost. And they're really good tips. So there you go. I mean, I think you have to care, though. And a lot of people don't care. They have a curiously passive attitude to, and one of the reasons the Santa Barbara Sense of Direction Scale works is that people are not ashamed to admit that they're bad at it, you know, and they would be ashamed, you know, oh, I'm illiterate, isn't that hilarious? Like, they wouldn't say that, but, oh, I get lost all the time, isn't that hilarious? Like, no, you should be ashamed of this. You should work on it. So I think it's also a motivational thing, but I don't know. We can find out. I don't have any data on this.